Okay, so good evening everyone. I am Shivani Dhok and I welcome you all for the week 12 tutorial for the course of Digital Signal Processing and its applications. So this is the last week tutorial for this particular course, and like every week, this week's tutorial will be divided into two parts. First, I'll have a quick recap of whatever we have covered in week 12, followed by the questions that are related to the week 12 content. Before I start with the recap of week 12 content, I would like you to note that if you have queries at any point of time, just stop me then and there, unmute yourself and ask the questions. Along with that, I will be having a summary session in this week and just before your exams. If you have any queries, then post those queries in the Q&A portal, Q&A tab in the NPTEL portal by tomorrow night, that is by 14th April night. Any questions that I get till tomorrow night, I will take them. Rest I shall not be able to take. Okay, so let's start with the recap of week 12 content. So first thing that we did in this week was revisiting the frequency domain concepts. So till the last week we were looking at filters and their representations. In this week we switched the gears, and then now we have started to look at the sampled version of frequency domain. So what do we mean by frequency domain sampling? So essentially, these frequency domain, when we take our DTFT, we know that the unique range of the angular frequency omega is minus pi to pi. Okay, and it is a continuous range. This particular range, whatever I have written here, is continuous. So you can figure out any point in frequency, any point in this given range, and have a DTFT defined for that particular angular frequency. Now, if you want to process this in computers, or if you want to perform filtering operations and all those things in computers, with the help of this DTFT, we can't do, because again, it has an infinite precision. So this can't be handled by computers. So what do? We sample this range into n points. So what we do? We sample this range into n points. Okay. And once we sample this range into n points, a result of this is we get carbon copies or replicas of the time domain signal at every integer multiple of n. Okay, so that kind of carbon copies we get in the time domain, and that get added to the original signal. So this brings an inherent periodicity to an aperiodic signal. So that signal was not periodic initially, but due to sampling in the frequency domain, now we are getting replicas of it getting added. Now since we are having replicas at every integer multiple of this n, so if the signal length is more than n, then we won't be able to recover or basically we will get a time domain aliasing. However, if the signal length L is less than n, then in that situation, we won't get any time domain aliasing, that there won't be any sort of overlapping and adding kind of phenomena happening. Now, another concept that is important in this particular thing is circular convolution, and that is directly related to what we call as a discrete Fourier transform. So this is a similar kind of convolution, similar to linear convolution, but we have a circularity in this particular thing. We will see it with the help of few examples coming up. And then we looked at a very important transform, which is the discrete Fourier transform. Yeah. So the discrete Fourier transform, it is given by x of k, and we obtained this using our DTFT by setting omega as 2 pi k by n. So what do we get? We get x of k as summation n running from 0 to n minus 1 x of n into e power minus j 2 pi k n by n. And this n can be anything greater than or equal to the number of greater than or equal to the length of your signal. You can find the DFT for n less than the length of signal, but it will cause time domain aliasing. Okay, now this we have, and then we have inverse DTFT. Inverse DFT, and the inverse DFT is given by x of n is equal to summation 1 over n. 1 over n summation n equal to equal to 0 to n minus 1 x of k e power minus j 2 pi k n by n. Is it clear? Any questions? Now this DFT and the circular convolution are related. So if we circularly convolve two time domain signals, then their DFTs get multiplied. That's the frequent. That is the circular convolution property of DFT. Okay, so that's all about the recap. If you have any questions, then let me know. Otherwise, I'll move on to the questions that I want to cover today. Okay, if there are no questions, then let me move on to the first question that I have planned to cover today. So let's start with the very basic question. That is, we will find the DFT of this given signal x of n. And here a key thing to note is this starts from n equal to 0. Okay. So this x of k, by definition, and another thing before I start, we'll find a 4-point DFT. Okay, so this x of k is given by summation n running from 0 to 3 x of n into e power minus j 2 pi k n by capital N is 4. So this particular thing is basically n minus 1, that is 4 minus 1 equal to 3. Okay, so now this can be simplified further as summation n running from 0 to 3 x of n into e power minus j pi k n by 2. Now I can simplify it further, that I'll get x of 0 plus x of 1 times e power minus j pi k by 2 plus x of 2 into e power minus j pi k and plus x of 3 into e power minus j 3 pi k by 2. Now let me substitute the value of x of 0, x of 1 and so on in this particular equation. So what do we get? X of 0 is 1. So we have 1 plus x of 1 is 2. So 2 into e power minus j pi k by 2 plus e power minus j pi k is basically minus 1 to the power k. And then we have x of 2 is 3 plus 4 into e power minus j 3 pi k by 2. Now let us find out this for different values of case. So this is my x of k, and we have a 4-point DFT. So this k belongs to 0, 1, 2, and 3. So let us try to do that. So what do we get? We get x of 0 as 1 plus 2 into e power minus j 0 by 2. So that is 1 plus minus 1 to the power 0 is 1 plus 3 plus 4 into e power 0, that is again 4. So this comes out to be equal to 10. Okay. Now we have x of 1, that is equal to 1 plus e power minus j pi by 2 plus 3 times minus 1 to the power 1 plus 4 times e power minus j 3 pi by 2. So 1 e power minus j pi by 2 is minus j, so that is minus 2j minus 3 plus 4j. So this comes out to be equal to minus 2 plus 2j. Then we have, in similar way, we can find x of 2, which will be equal to 1 plus 2 into e power minus j pi k is equal to 2 plus minus 1 to the power 2 into 3 plus 4 into e power minus j 3 pi. So this is equal to 1 minus 2 plus 3 minus 4, and this comes out to be equal to minus 2. And finally, we have x of 3, capital X of 3 as 1 plus 2 into e power minus j 3 pi by 2 plus minus 1 to the power 3 into 3 plus 4 into e power minus j 3 pi 3 by 2. And when we simplify this comes out to be equal to 1 plus 2j minus 3 minus 4j. So this comes out to be equal to minus 2j. So therefore, my x of k is a sequence that start with 10 for k equal to 0. Then it is minus 2 plus 2j minus 2 minus 2 minus 2j. Is this clear? Any questions? Any questions at this point? Okay, if there are no questions, then let me move on to the next question. So here it says that it says that consider a train of unit impulses given by P of n equal to this. So these are train of impulses with impulse at every integer multiple of n. Okay. So what it says, consider a train of impulse given by this equation where n is greater than 1 is the period of this impulse. That simply means whatever I have written here, that an impulse is present at every integer multiple of capital N. Now it says that, or rather it's asking us what is the nature of its DTFT. And here we have 4 options. So the four options are a DC waveform, a single impulse, a train of impulses with period 2 pi, and a train of impulses with period 2 pi by n. Okay. So now this is basically a periodic signal, and we can't find the DTFT directly. We have seen a similar case for continuous time also, where we had found the CTFT of continuous time train of impulses, and in that also we had taken a different approach, and the different approach was it is dependent on the discrete Fourier series, or rather the Fourier series coefficients. So for this also we will take two-step approach. So here the step 1 will be finding discrete time Fourier series coefficients, that is AKs, and step 2 is find DTFT using, let's say, P of omega. Let P of omega be the DTFT of P of n, is equal to 2 pi summation n running from k running from minus infinity to infinity, a k's delta omega minus omega naught k, where omega naught is the fundamental frequency. Okay, so these are the two steps that we will be doing. So now let us start one by one. So let's start with the step 1, which is finding AKs, and that is given by, so this AKs are given by 1 over n summation n running from 0 to n minus 1 P of n into e power minus j k omega naught. And what is omega naught? Omega naught is 2 pi by n, where n is the period. So let me substitute it back here. So what do I get? 1 over n summation n equal to 0 to n minus 1 P of n into e power minus j 2 pi k n by n. Okay. Now what is P of n in this range? P of n is train of impulses like this. So if I have n from 0 to n minus 1, in that range my P of n is simply delta n. Okay. So here we have 1 over n summation n running from 0 to n minus 1 unit impulse into e power minus j 2 pi k n by n. Now what we will have? Now we'll use a shifting property of this equation. So here we will get delta n into e power minus j 2 pi k 0 by n, which is equal to delta n. So if I substitute it back, I'll get 1 over n summation n running from 0 to n minus 1 delta n into 1, and summation of the train of impulses over its duration, or rather in 0 to n minus 1, sum of this unit impulse is 1. So what we get is 1 over n. So what I just said is this summation is equal to 1. Okay. So now I have this, I have AKs which I wanted to find, and the next step is to substitute these AKs to find the DTFT. So let us do that quickly. So now we will do our step 2. Finding P of omega. So what do we get? P of omega is 2 pi summation k running from minus infinity to infinity ak delta omega minus k times omega naught, and omega naught we have seen it is equal to 2 pi by n. K 2 pi by n. Okay, so now what were our AKs? We have seen that AKs come out to be equal to 1 over n. So this is equal to 2 pi summation k equal to minus infinity to infinity. AKs are 1 over n into delta omega minus k 2 pi by n, which comes out to be equal to 2 pi by n summation k running from minus infinity to infinity delta omega minus k times 2 pi by. Okay, so now what do we see? What do we observe here? So this part, scaling, you forget the scaling. Scaling is not a function of frequencies. So this particular part is again a train of impulses. And what is the period? Period of this train of impulse? The period is, it is located at every integer multiple of 2 pi by n. At every integer multiple of 2 pi by n, an impulse is located. So therefore its period is 2 pi by n. So now what did we see? We saw that the frequency domain or the DTFT of a train of impulse with period n has a DTFT, a train of impulse with period n has a DTFT again as a train of impulse in frequency domain with period 2 pi by n. Okay, so let's go back to our options. So the option that fits is this particular one. That is, it is a train of impulses with period 2 pi by n. Is this clear? Any questions? Any questions till this point? Okay. If there are no questions, then let me move on to the next question. Okay. So here the question says that consider the given statement where x tilde of omega is n over 2 pi x of omega into p of omega, and this has its inverse DTFT as x tilde of n, which is n over 2 pi x of n convolved with p of n. Here x and p are as defined in the previous question. We assert that the given statement can be used to demonstrate the occurrence of aliasing. Is this assertion true or false? Okay, so what it says that we have this particular relation here. It's saying that can we use to understand the time domain aliasing with the help of this particular relation. Okay, so for time domain aliasing we need to focus on this particular thing here. Okay, So in frequency domain, when, okay, so let me just start it in this way. So what is given to us is this: x tilde of omega is 1 over 2 pi x of omega into p of omega. So what is happening here? Here, this is a train of impulse. We have seen this is a train of impulse that gets multiplied to this particular signal. So if you recall, when we were doing time domain sampling, at that point also, we were focusing on, or when we were doing sampling, we multiplied the signal, the time domain signal, with a train of impulse. So whenever we are multiplying a given signal with the help of a train of impulse, that shall lead to sampling. So this particular equation here is basically allowing us to do sampling in time, sampling in frequency domain. Okay. So let me write it down for you. So this equation here is basically sampling in frequency domain. Okay. So here we are having sampling in frequency domain. And by the convolution, time convolution property, its inverse DTFT is x tilde of n, which will be n over 2 pi x of n convolved with p of n. Okay, so let's do that. X tilde of n is n over 2 pi x of n is as it is convolved with p of n. What was our p of n in previous question? P of n was summation k running from minus infinity to infinity delta n minus k n. Summation k running from minus infinity to infinity delta n minus k capital N. Now let me use the distributive property of convolution. So we'll get 1 over 2 pi summation k running from minus infinity to infinity x of n convolved with delta n minus k capital N. So this comes out to be equal to n over 2 pi summation k running from minus infinity to infinity x of n minus k. Okay. So we are getting something like this. So what is happening here? Just a moment. Okay, so what is happening here? We are getting replicas of x of n. So basically, we are getting here in this particular summation, we are getting replicas of x of n at every integer, multiple of n. Okay, so let me add a page here. So what I will do is, let's say we have an x of n, the loss of generality, something like this. We use different colors. We have this x of n, and then we have, let's say, something like this. This is L, L minus 1, 0 to L minus 1. And what is happening is, this is, let's say, some n, whatever in negative axis also same thing will happen, and this is x tilde of n. So what is going to happen? N minus 1, sorry, 2n, 3n, and so on. We have replicas of this. Then again it will simply repeat. It will just simply repeat it. Like this, like this, and so on. So now here is the case where my n is greater than L. Okay, or let's say greater than or equal to n. If n is less than L, then I will have some sort of overlap. So for example, if the signal is something like this, then everywhere I'll go on having overlapping. Signals, or rather replicas, will overlap. Okay, which means that this will give me time domain aliasing. And this kind of phenomena is happening when we sample in frequency domain. That is when we move from DTFT to DFT. Exact same thing is happening. That's why we get replicas in time domain when we are finding the DFT. Okay. So what is the conclusion now? The conclusion is, if length of signal, or rather length of x of n, say L, is less than n, or less than or equal to n for that matter, there will be no aliasing in time domain. If length of x of n, that is L, is greater than n, then we have aliasing in time domain. So what does this mean? This means that the given assertion, or rather the given statement, helps demonstrating the time domain aliasing. Okay. Okay, any questions? Any questions at this point? Any questions? Okay, if there are no questions, then let me move on to the next question. Just a minute. Okay. There's a small typo here. This is for. Yeah. So it says that assume for a moment that x of t is a continuous time real and non-negative signal with a non-negative and real Fourier transform. That is this particular thing. If it is sampled at an t equal to ns, where ts is the sampling duration, and if x of n represents the signal of its samples, the sequence of its samples, then following statements may be true. So we have one relation here, then we have another relation here, and then it says that the equality in above two relations holds if the signal is band limited and sampled at a frequency greater than the Nyquist rate. And next is equality holds even if the signal is not band limited. Okay, so looking at this particular question, working in time domain seems difficult. So now what we will do, we'll take use of the frequency domain representations, and we'll try and use the very important property of BTFT and CTFT, which is known as the Parseval's theorem. I'll list down the Parseval's theorem whenever it is necessary. Okay, so let's start. So what is given to us? Given to us is x of t. This is a time domain, continuous time signal. Okay, and let x tilde t be the sampled version of x of t. That is, x tilde t is simply x of t multiplied by p of t, where p of t is given by summation k running from minus infinity to infinity delta t minus k times ts, where ts is sampling duration. Okay, so now using the time multiplication property, of x of t, sorry, of CTFT, x tilde of omega is equal to x of omega convolved with p of omega and scaled by a factor of 2 pi. And we have seen long back when we discussed sampling, we had seen that P of omega comes out to be equal to 2 pi by Ts summation k running from minus infinity to infinity delta omega minus k times omega s, where omega s is simply 2 pi by Ts. This you can obtain in the exact same way what we have done in the question 2 of this week. Just you need to use the continuous time Fourier series and the continuous time Fourier transform. Okay, now let me substitute this in this particular equation. So what do we get? Therefore x tilde of omega is equal to 2 pi into 2 pi by Ts summation k running from minus infinity to infinity delta omega minus k times omega s convolved with x of omega. Sorry, it's divided by this. So what do we get? We get 1 over Ts so we get 1 over Ts summation k running from minus infinity to infinity x of omega minus k times omega s. Okay. So this is my x tilde of omega. Okay. This is my equation 1. Now what I'll do, now if I go back here somewhere, I get a relation which is something related to magnitude of x of t square. Okay. Now it's very difficult to figure out what is happening from here, or rather we know the Parseval's theorem has a relation with magnitude of x square and so on. So what I'll do is I'll square these two things. I'll take x square, x tilde square of omega, that will be 1 over Ts square, and summation k running from minus infinity to infinity x of omega minus k times omega s whole square. Now since this particular x of omegas are positive, this should be greater than or equal to 1 over Ts square summation k running from minus infinity to infinity x square of omega minus k times omega s. Okay, so now another thing, since this is these are positive, so this is coming from x of omega greater than 0 for all omega. Since these are positives, this is equal to its magnitude, so we get magnitude x tilde square of omega to be greater than or equal to 1 over Ts square summation k running from minus infinity to infinity magnitude of square of omega minus k times omega s, or this I can write as like this. Okay, so now what we can do, I can shift this 1 over Ts this side, so what I get Ts square into magnitude of x tilde of omega square is greater than or equal to summation k running from minus infinity to infinity magnitude of x of omega minus k times omega s square. Okay, so now what we will do, now we will integrate over the unique range of omega, that is omega belonging to minus omega s by 2 to omega s by 2. Okay, so what I get? I get Ts square integral minus omega s by 2 to omega s by 2 magnitude of x tilde of omega square d omega is greater than or equal to integral minus omega s by 2 to omega s by 2 magnitude of x of omega minus k omega s. Sorry, there's a summation here which I forgot. Summation over k equal to minus infinity to infinity magnitude of x of omega minus k times omega s square d omega. Okay, so let me number this as my equation 1, and now we'll handle the left hand side and right hand side individually. So let us take the left hand side first. So what is it? It is Ts square integral minus omega s by 2 to omega s by 2 magnitude of x tilde square of omega square d omega. Okay. Okay. So now what we can do is this particular thing here, since we are integrating it over the unique range, this is greater than or equal to Ts. Just a moment, what am I doing? Yeah, so okay, wait a minute. So this thing here, we have Ts into the, before that what I'll do, I'll multiply, sorry, I divide by 2 pi on both the sides like this. So I have a 2 pi here. Now we have this omega s as 2 pi sampling frequency fs, or rather 2 pi by ts. Okay. And this I can also write as, oh sorry, 2 pi f by, yeah, we have this relation, yeah. And then we have omega as 2 pi f by fs, which is omega by fs. Now I can multiply by 2 pi on numerator and denominator, and this 2 pi fs, as we have seen, is simply my omega s. So this omega is 2 pi capital omega by omega s. Okay. So now what we will do, we will replace omega with omega into omega s, little omega into capital omega s over 2 pi. Okay. So if we do that, what do we get? This part will basically become my x of omega, or rather this will be x tilde of omega by ts, which is simply my x tilde of omega, or rather x of omega, and the limits will become, omega will now vary from minus pi to pi. So this becomes ts square by 2 pi, and This d omega is basically 2 pi omega d omega by omega s, which is simply Ts. So 1 over Ts into integral minus pi to pi magnitude of x of omega little omega square d omega. So this is basically dTft of sampled version, that is x of n. And using Parseval's theorem, this gets cancelled. Using Parseval's theorem, let me write it properly. This is not right. So LHS is Ts into 1 over 2 pi integral minus pi to pi magnitude of x of omega square d omega. And this is equal to Ts into summation n running from minus infinity to infinity x of n, magnitude of x of n square. And this is using Parseval's theorem. Okay. Now we will move on to the RHS. What is RHS? RHS is 1 over 2 pi integral minus omega s by 2 to omega s by 2 summation k running from minus infinity to infinity magnitude of x of omega minus k times omega s whole square d omega. Now if I interchange the order of summation and integration, what I get 1 over 2 pi summation k running from minus infinity to infinity integral minus omega s by 2 to omega s by 2 magnitude of x of omega minus k times omega s whole square d omega. So here I'll have k. So this is equal to 1 over 2 pi just a minute. Yeah, 1 over 2 pi integral minus infinity to infinity magnitude of x of omega square d omega, which is equal to integral minus infinity to infinity magnitude of x of t square dt. Again, this is Parseval's theorem. And this Parseval's theorem for continuous time Fourier transform. So if I substitute it back, what do I get? We get what do we get? We get Ts into summation n running from minus infinity to infinity magnitude of x of n square is greater than or equal to integral minus infinity to infinity magnitude of x of t square dt. And when will this inequality hold with equality? This will hold when the first inequality holds. That is, when this holds. And when will this hold? This will hold when the cross terms are 0. That means it will hold when the signal is band limited. This will hold with equality if signal or x of omega is band limited and sampled at omega s greater than or equal to 2 times omega n. This is the maximum frequency. Is it clear? So what is the final answer that we get? We get that this is correct and equality holds if the signal is band limited and sampled at a frequency greater than the Nyquist rate. Okay, is it clear? Any questions at this point? Okay, if there are no questions, then let me move on to the next question. So here we are given a common data. So it says that the endpoint DFT of a endpoint sequence x of n is given by this equation here. And we'll be using this equation frequently in the questions from 5 to 7 and maybe few questions ahead of them. Okay. Okay, so let's start with the first question. So here it says that consider a 4 endpoint sequence y of n. Okay, so what do we have? We have a 4 endpoint sequence y of n and it is defined as y of n is equal to x of n. So this y of n is equal to x of n for n in the range of 0, 1 and so on till n minus 1 and it is 0 otherwise. And this y of n is valid for n in the range of 0, 1 and so on till 4n. So how does this signal look? This y of n looks something like this. So first n samples come from x of n. So we get x of 0, x of 1 and so on till x of n minus 1. So this starts from n equal to 0 and then we have 0 starting from little n equal to capital N, 0 and so on till 0 and this corresponds to 4n minus 1. Okay, so this is how our y of n looks like. Now what it says is if y of k denotes the 4n point DFT. So this y of k, it denotes the 4n point DFT of this little y of n. Then x of k is equal to 4 times, x of k is equal to y of 4k and we need to figure out if this is true or false. Okay, so let's do it step by step. So what is x of k? So x of k is endpoint DFT of x of n. And where is this coming from? This is coming from this fact here. Okay, so we need to use this. And this is given by x of k is equal to summation n running from 0 to n minus 1 x of n into e power minus j 2 pi k n by capital N. Okay, so we have this thing here. Now we have y of k and this is 4 endpoint DFT of y of n. Okay, so what does it look like? So therefore y of k is equal to summation n running from 0 to, now here my n I need to replace by 4n, so we have 4n minus 1 y of n into e power minus j 2 pi k n by 4n. This is equal to summation n running from 0 to 4n minus 1 y of n into e power minus j pi k n by 2n. Okay. Now by whatever is given to us, for this y of n is non-zero only for first n samples, and after that it is 0. Okay, so we can split this into two parts. So first will be, we can write it as summation n running from 0 to n minus 1 y of n into e power minus j pi k n by 2n plus summation n equal to capital N to 4n minus 1 y of n into e power minus j pi k n by 2n. Okay, so now in this region from 0 to n minus 1, this y of n is equal to x of n, and in this region this y of n is equal to 0. So this entire summation goes to 0. So only surviving summation is the first one. So what we get, y of 4k, sorry, y of k is summation n equal to 0 to n minus 1 x of n into e power minus j pi k n by 2n. So now we have y of k, but we are not interested in y of k. We are interested in y of 4k. Okay, so now what we will do, we'll use this equation to find y of 4k. So therefore, y of 4k is equal to summation n running from 0 to n minus 1. This remains as it is. This is not a function of k. X of n is also not a function of k into e power minus j pi. Now this k has to be replaced by 4k n by 2n. So this gets cancelled and we get a 2 here. So now what we have y of 4k equal to summation n equal to 0 to n minus 1 x of n into e power minus j 2 pi k n by n. And if you observe, this is exactly the same equation as x of k. So this is equal to our x of k. So what do we get? We get x of k is equal to y of 4k. So we get x of k is equal to y of 4k. So therefore this statement is true. Any questions till this point? Any questions? Okay. If there are no questions, then let me move on to the next question. So this is the next question. It says that consider another 4n point sequence z of n defined as x of z of n is equal to x of n for n equal to 0 to n minus 1, and z of n is equal to x of n minus capital N for n equal to 2n, 2n plus 1 and so on, and it is 0 otherwise. Okay. Okay, just a moment. I think I made some mistake here. Yeah, there should be a 2 here. Fine, this looks okay now. Yeah. Okay, so this is the question that we have. So now what is given to us? We have z of n is equal to x of n for n in the range of 0, 1 and so on till n minus 1, and it is x of n minus 2n for n belonging to 2n, 2n plus 1 and so on till 3n minus 1, and it is 0 otherwise. Okay. So now let us see. So okay, so this is the z of n that is given to us. What it says is if zk is the 4n point DFT of this signal, uh, then which of the following is true? So we have these 4 options. So these are basically trying to figure out the relation between zk's and y of k's. So let us try to do that quickly. Okay, so now let us first understand how this zk look like. So the z of k or z of n is basically again a sequence which is equal to x of 0, x of 1 and so on till x of n minus 1. This is at 0, and then we have zeros, sorry, and then we have zeros here, and these are n zeros. This is basically n, and this is basically to n minus 1, and then we have, sorry, and then we have x of 2n, sorry, x of 0, this is at 2n, then x of 1 and so on till x of n minus 1. This is at 3n minus 1. Then again we have zeros. This is at 4n minus 1. Okay. Now I can write this as a sum of two different sequences. So I can write this as x of 0 and so on till x of n minus 1. And then I can have zeros from n to 4n minus 1, plus I can have zeros, and this is from 0 to till 2n minus 1, and then I can have x of 1 and so on till x of n minus 1, and this is at 2n, this is at 2n minus, sorry, 3n minus 1, and then again I can have zeros, and this is at 4n minus 1. Okay, so now if we observe carefully, this particular sequence which I highlighted in green is exactly the same sequence that we had in the previous question, which is my y of n. So this is exactly the same sequence that I am getting in the next question, this question as well. So this particular thing here is my y of n. Now this particular sequence, again what we have, it is 0 everywhere otherwise. So this particular sequence is basically the y of n if I shift it rightwards by a factor of 2n. So basically this sequence which I just highlighted, this is basically equal to y of n minus 2n, n minus 2 capital N. Okay, so now what I can write? I can write as y of n, sorry, z of n is equal to y of n plus y of n minus 2n. Okay. Now what is, so we know that DFT of y of n is y of k. What is DFT of this? Let us try to figure out. So DFT of y of n minus 2k, sorry, 2 capital N, will be equal to summation n running from 0 to 4n minus 1 y of n minus 2n e power minus j 2 pi k n by 4n. This is equal to summation n running from, this is a periodic thing, so I can write it as 0 to 4n minus 1 y of n into e power minus j 2 pi k n plus 4n by, sorry, 4n, 2n by 4n. I'll request you to see this proof nicely in your free time. So this is basically e power minus j 2 pi k to n by 4n into summation n running from 0 to 4n minus 1 y of n into e power minus j 2 pi k n by 4n. This is equal to e power minus j, this gets cancelled. I have minus j pi k, and also gets cancelled, pi k into y of k. So now I can substitute it back here. So what I get? We get z of k is equal to y of k plus e power minus j pi k y of k. E power minus j pi k is minus 1 to the power n k. So y of k I can take common. So 1 plus e power minus, sorry, I can write it as minus 1 to the power k. Okay, so now I have zk's here. So now what I can do? Okay, so now let me go back to the options. So what I have, zk is 1 minus 1 to the power k, 1 plus minus 1 to the power k into y of k. So this is not there. This also is not there. Z is not 0 even if I shift it. And now we have z of 4k to be found out. So what I get? Z of 4k is y of 4k into 1 plus minus 1 to the power 4k. Now 4k will always be an even quantity, and minus 1 to the power any even quantity is 1. So this comes out to be equal to y of 4k. Now remember, into 2. Yeah. So now remember, in the previous question we had found out y of 4k. And we had seen that this y of 4k is equal to x of k. So what we get? So this now becomes 2 times x of k. So this is coming from the previous question. Okay, so we have z of 4k equal to y of k, 2 times x of k. So this is what we get, and this is the final answer. Is it clear? Any questions at this point? Okay, if there are no questions, then let me move on to the next question. Okay. So the question here says that let x of n be a 4-point sequence, that is capital N equal to 4, and let x equal to x0, capital X vector equal to x0, x1, x x2 and x3 transpose, and let little x be little x0, x1, x2 and x3 transpose. This is basically the vectorized form of my DFT and DTF and my original signal. So now they say that in this vectorized form, we can write this capital X vector as a matrix M multiplied by this little x vector. And then we need to figure out the relation between its determinant. Okay. Okay, so let us try to do that. Okay. Okay. So this X is basically a vector that stacks the DFT, the 4-point DFT of the signal X of n. So this vector X, I'll denote X vector with an underscore for the particular alphabet. So this is basically a vector that stacks all the 4 values of 4-point DFT. So this X of k is given as summation little n equal to 0 to capital N minus 4, where n is 4, so 4 minus 1 is 3, x of n into e power minus j 2 pi k n by n, capital N is again 4. So this we can write as summation n equal to 0 to 3 x of n into e power minus j pi k n by 2. So now I can simplify this as x of k equal to x of 0 plus e power minus j pi k by 2 x of 1 plus e power minus j pi k x of 2 plus e power minus j 3 pi k by 2 x of 3. Okay. So therefore x of 0 is equal to x of 0 plus x of 1 plus x of 2 plus x of 3. Similarly, x of 1 is equal to x of 0 as it is plus e power minus j pi by 2, that is minus j x of 1 plus e power minus j pi, so that is equal to minus 1, so minus x of 2 plus e power minus j 3 pi by 2 x of 3, so that is plus j x of 3. Now we have x of 2, that is equal to x of 0 as it is plus e power minus j pi, which is minus, so minus x of 1 plus e power minus j 2 pi, so that is 1, so plus x of 2 plus e power minus j 3 pi k x of 3, so that is minus x of 3. And then we have capital X of 3 as x of 0 plus j times x of 1 minus x of 2 plus minus j times x of 3. So now let us stack it in a vector form. So we have here x of 0, x of 1, x of 2 and x of 3. This is equal to a matrix M, a matrix, and then we have here x of 0, x of 1, x of 2 and x of 3. So now for x of 0, capital X of 0, x of 0 gets multiplied by 1, this gets multiplied by again 1, this also gets multiplied by 1 and this also gets multiplied by 1 and then get added. So we have 1, 1, 1, 1 here. Now for x of capital X of 1, we have x of 0 getting multiplied by 1. So we have 1 here. Then x of 1 gets multiplied by minus j. So minus j. X of 2 gets multiplied by minus 1. So we have minus 1. And again x of 3 gets multiplied by j. So we have a j here. Now similarly, for capital X of 2, x of 0 gets multiplied by 1. X of 1 gets multiplied by minus 1. X of 2 gets multiplied by 1. And x of 3 gets multiplied by minus 1. Similarly, x of 0 gets multiplied by 1, x of 1 gets multiplied by j, x of 2 gets multiplied by minus 1, and x of 3 gets multiplied by minus j. Okay, so we have something like this. So this is x, which is equal to a matrix M multiplied by a vector little x that stacks on the time domain values. Now what we need to figure out? We need to figure out the determinant of this matrix M. This is a 4 by 4 dimensional matrix. Finding determinant is cumbersome. So what we will do, we'll try to use the properties of DFT and try to see if we can do anything with this. Okay. So now let us say that x of n has a n-point DFT as x of k. So this basically is equivalent to x equal to m times x. Okay. Now what happens if I find the DFT of x of k? That is, what if I have x of n, capital X of n, then what is its DFT? Let us try to figure out. Let's say it is some x tilde of k, capital X tilde of k. So this x tilde of k is basically equal to summation n running from 0 to n minus 1 x of n into e power minus j 2 pi kn by. Okay, so we have this. Now what we can do, so I can write this as summation n equal to 0 to n minus 1 capital X of n into e power j 2 pi minus k n by n. And if I add plus n, it nothing happens because this simply gets cancelled and we get 1, and e power j 2 pi 1 is equal to 1. So now what we get, or rather 2 pi n. So this is equal to summation n equal to 0 to n minus 1 x of n into e power j 2 pi n minus k n by n. So this comes out to be equal to, I can multiply and divide by n here, summation n equal to 1 to n minus 1 x of n into e power minus j 2 pi n minus k by n by n. Now this trick we did because we know that this x of n is valid only from 0 to n minus 1. Okay, and due to inherent periodicity it gets repeated, but still we'll try and stay in the range of 0 to n minus 1. For that we did this particular trick. Okay, and this particular thing here is basically x of n, okay, not this entire thing, is basically x of n minus k. Okay, and we have a n multiplied here. So this comes out to be equal to n times x of n minus k. So what do we have? First thing that we have is x of n has an n-point DFT as x of k, This is equal to x as multiplied by x equal to m times little x. Then we have this x of k, we have n point DFT. So here what we get n times x of n minus k. This is equivalent to m times x square. Okay. Now what we will do, third one is what we will do, we'll take n times x of n minus k, and we will find n point DFT of this thing. So what we will get, we'll get n, and since it is a shifted version, so I'll get n times x of n minus some k, and this is basically m cube of x. So this is coming from time shift property of DFT. And finally, what I can do is I can take n times x of n minus k, and I can find its n point DFT. So that will be n square, and DFT of x of n minus k will be simply little x n minus n plus k, which is equal to x of k times n square. And this thing here is basically m to the power 4 x. Okay. So what are we getting? We have x here. We do a DFT one time, so we get m times x. Then we do a DFT another time, we get m square times x. And then we get, third time we get m cube times x. And then we get m to the power 4 times x. And this m to the power 4 times x is basically n square x. Okay, so now if I equate these two, what do I get? We get m to the power 4x is equal to n square x. I can take both on this side. So we have m to the power 4 minus n square identity matrix into x is equal to 0. Now this x is not 0, which means that this should be 0 or singular, and which means that determinant of this should be equal to 0, or rather this should be equal to 0. So we have m to the power 4 minus n square I is equal to 0. So we have m to the power 4 equal to n square I. So determinant of m to the power 4 is equal to n to the power 2n. So therefore magnitude of determinant of m is equal to n to the power 2n by 4. So that is equal to n to the power n by 2. So for our case, n is equal to 4, which means that determinant of m in magnitude is equal to 4 to the power 4 by 2, that is 4 square, which comes out to be equal to 16. Is it clear? Any questions? So what we have as our final answer, determinant of this m is equal to 16. Any questions at this point? Any questions? Okay. If there are no questions, then let me move on to the next question. Okay. So this is a common data for question number 8 to 10. And it says that consider a signal x of n. Note that given by this signal, the sequence, and note that x of 0 is 1. So here it is 0. And this is, let's say, 3. And x of n is 0 otherwise. So what it's saying is, we are given a sequence x of n, that is 1, 2, 2, 3, something like this. And this is the information for question number 8 to 10. Now it says that what is the first question that we need to handle is, what is the 4-point circular convolution of x of n with itself? So what is circular convolution? So circular convolution is given by y of n, which is equal to x of n convolved circularly, n-point circular convolution with x of n as it is. And this is basically equal to summation L running from 0 to n minus 1 x of L into x of n minus L modulo n. Okay, so this is how it looks. This is the modulo operator. Okay, so now just looking at this math, this equation and this particular way of finding it and modulo operator, it becomes very cumbersome to solve. So what we will do, we'll try to use trick or some representation, different representation, or some pictorial representation to find this. So for that, what we do is, we draw a circle. We draw two circles basically, the inside circle and the outside circle. The inside circle will have the values that correspond to this x of L. Okay, so this inside circle will correspond to x of 0, which is here, x of 1, x of 2, and x of 4. So what is it? X of, let me write it down here, x of n is 1, 2, 2, 3. So here we'll have 1, 2, 2, 3 as it is. And now we need to find the circular convolution of this signal with itself. So now we have taken care of this quantity. Now we will take care of this quantity. So now if you observe, this is like a flipped signal. So now if this is the direction of my correct or rather positive direction, actual direction, if I take an opposite direction, then that will be basically the direction of flipped signal. So for L equal to 0, for n equal to 0 rather, I'll have it flipped. So 1 second, made a mistake here. This is not n, this is little n. Yeah, so if my n is equal to 0, I have a flipped 1. So then I'll have 1, 2, 2, 3 as it is. Now what we need to do? We need to multiply these point by point, which are the nearest one, like this, and add them. Okay. Okay. So what do we get? So y of 0 will be equal to this multiplication, that is 1 into 1, plus this multiplication, that is 2 into 3, plus this, that is 2 into 2, plus this quantity, that is 2 into 3. So this comes out to be equal to 1 plus 6 plus 4 plus 6, and this is equal to 17. Okay. Now for y equal to 1, so here my n equal to 0, here my n will be equal to 1. The inner circle remains as it is, so that will be 1, 2, 2, 3. But now when I have n equal to 1, I am shifting it rightwards by a 1 unit. So what I'll do, I'll shift it rightwards like this in the proper direction by 1 unit. So this one will now appear here. So what I get, I'll get a 1 here, then 2, 2, 3. And now I'll again multiply it like this. And what I get y of n is equal to 2 into 1, that is 2, plus 2 into 1, that is again 2, plus 2 into 3, that is 6, plus 2 into 3, that is again 6. So this comes out to be equal to 16. Okay. So now I have reached till n equal to 1. Now let us figure out what happens when my n equal to 2. Again same story, the inner circle remains as it is. Now I have shifted the original signal by 1 unit in this direction. So we had got 1, 2, 2, 3 here. Now again I'll shift it in this direction by 1 unit. So now this 1 should appear here. So what I get? Now I get a 1 here, then 2, 2, 3, and now I'll have a multiplication like this. Okay. So therefore, y of 2 is equal to, so let me write it properly, this is y of 1. Okay. So this y of 2 will be equal to 2 into 1, that is 2, plus 2 into 2, that is 4, plus 2 into 1, that is 2, plus 3 into 3, that is 9. So this comes out to be equal to 17. And finally, so what I'll do, I'll just push this little up. This is for n equal to 2. I don't want to add additional page. Yeah, okay. Now finally we'll figure out what is for n equal to 3. Again same story, inner circle remains as it is. And then what do we get? Yeah. So now we have reached till this point. Again we'll shift it by 1 unit here. So we'll get 1, 2, 2, 3. And now we will multiply element by element like this and add them. So what do we get? We get y of 3 as 3 into 1, that is 3, plus 2 into 2, that is 4, plus 2 into 2, that is again 4, plus 3 into 1, that is again 3. So if I simplify this, this comes out to be equal to 14. So what do I get? I get a sequence of y of n, which is equal to y of 0 is 17, y of 1 is 16, y of 2 is again 17, and y of 3 is 14. Okay, is it clear? Any questions? Any questions at this point? So this is how we find circular convolution with the help of this circular ring representation. This is a simpler way to handle circular convolution than looking at the difficult or that cumbersome equation. Okay. If there are no questions, then let me move on to the next question. So here it says that we need to find the 10-point circular convolution of x of n. What we will do, we'll repeat the same exercise, but now I will have n equal to, or capital N equal to 10. So for that, what we can do is we can append so we had 1 2 2 3 like this, so we had this 4 values. Now to make this 4 points 10 point, we can append 6 zeros like this. So this is the 10-point sequence, and now we need to find the circular convolution of this with itself. Again, same trick we will do. We'll draw a circle. In that, the innermost circle will have x of n. That will be 1 2 2 3 and remaining all zeros, and the outer circle will have the flipped version of this x of n, that is 1 2 2 3, and again we have zeros like this, and then we will multiply element by element like this, and then add them to get the final answers. Okay, so this is what we will be doing, and this has to be done for 10 values, that is n equal to 0 to n minus 1, that is 0 to 9. Okay, so now we first do it for n equal to 0. So this is the situation for n equal to 0. We have flipped it, but we know we don't have to shift it. So now what we can do, we'll multiply it element by element like this. Okay, so what we get y of 0 as 1 into 1, that is 1. Then we have plus 2 into 0, that is 0. Then again 2 into 0, which is again 0. 3 into 0, 0. Zeros, 0, 0. Then again we have 3 into 0, 0. 2 into 0, 0. And 2 into 0, 0. So y of 0 is equal to 1. Now we need to figure out what is y of 1. Now for y of 1, we'll shift this outer circle by 1 unit in the clockwise direction. So what we will get? So we were here. Now this 1 will now be coming at this location. So we'll have 1, 2, 2, 3, 0, 0, 0, 0, 0, and 0. Okay. So now again we will multiply it like this, element by element. Okay. So now what we get? We get y of 1 as 2 into 1, that is 2, plus 2 into 1, that is 2. Then we have plus 2 into 0, 0, 3 into 0, 0, 0 into 0, again zeros, 0, 0. And then we have 3 into 0, 0 and 2 into 0, 0. So y of 1 is basically 2 plus 2, which comes out to be equal to 4. Now we have reached till this point. Now we'll again shift it by 1 unit like this. So now we'll come at this particular position. So we were here, now we'll move it here. So now we will have 1, 2, 2, 3, 0, 0, 0, 0, 0, 0, and this is for n equal to 2. Okay. So now we'll do the same story. We'll multiply element by element like this. So what do we get now? We get y of 2 is equal to 2 into 1, 2, plus 2 into 2, 4, plus 2 into 1, 2. Just a minute. 2 into 1, 2. So this comes out to be equal to 8. Okay. Now this is for n equal to 2. Now we'll repeat the same thing for n equal to 3. We have reached till this point. Now we'll shift it by 1 unit. So we'll move it here. So what do we get? We'll be here 1, 2, 2, 3, 0, 0, 0, 0, 0, 0. Okay. So now what we have 3 into 1, 3. So we have y of 3 equal to 3 into 1, 3 plus 2 into 2, that is 4, plus 2 into 2, that is 4, plus 3 into 1, that is 3. Then we have plus 0 into 0, 0, 0 into 0, 0, 0 into 0, 0, 0, 0 and 0. So this comes out to be equal to 14. Okay. So we have reached till n equal to 3. Now next we will do for n equal to 4. Now where we were, so we have the starting point at n equal at here. So now we'll shift it here. So now we will come at this particular location. So we'll give 1, 2, 2, 3, 0, 0, 0, 0, 0, 0. Something is happening apparently. Yeah. Okay, it's okay. A y of 4. Then we have, what do we have? We have 0 into 1 as 0, plus 3 into 2, which is 6, plus 2 into 2, that is 4, plus 3 into 2, that is 6, plus 1 into 0, 0, 0 into 0, 0, 0 into 0, 0, 0 into 0, 0, 0 into 0, 0, and again 0 into 0, 0. So this comes out to be equal to 16. Now let us do it for n equal to 5. We'll again move this one in this direction. So what we get, 1, 2, 2, 3, 0, 0, 0, 0, 0, 0. Oh, sorry. 1, 2, 2, 3, 0, 0, 0, 0, 0, 0. Okay, so now we have y of 5, which is equal to, this is 0 into 1, 0, 0 into 2, 0, 2 into 3, it is 6, plus 2 into 3, it is 6. Then we have 2 into 0, 1 into 0, 0 into 0, 0 into 0, 0 into 0, and 0 into 0. So this comes out to be equal to 12. Next, we will find out for n equal to 6. Move, shift this little bit up. Yeah, okay. Now my 1 was here. We'll shift it by 1 unit here. So what do we get? We have 1, 2, 2, 3, 0, 0, 0, 0, 0, 0. So this is y of 6, which is equal to 0 into 1, 0, 0 into 2, 0, 2 into 0, 3, 2 into 0, 0, 3 into 3, 9, plus 2 into 0, 0, 2 into 0, 0, 1 into 0, 0, 0, 0, and 0. Okay, now we'll again shift it by 1 unit. So now what we will get? We'll get our 1 here, 1, 2, 2, 3, 0, 0, 0, 0, 0, 0. So now what we get? We have y of 7 here. So we are finding it for n equal to 7. So we get 0 into 1, 0, 0 into 2, 0, 2 into 0, 0, 3 into 0, 0, 3 into 0, 0, 2 into 0, 0, 2 into 0, 0, 1 into 0, 0, and again we have remaining all as 0. So this y of 7 comes out to be equal to 0. Now similarly, we'll figure out what happens when we shift it by 1 unit more. So now we are here, we'll move it to this point. So we will be here, 1, 2, 2, 3, 0, 0, 0, 0, 0, 0, and this is for n equal to 8. Now again what we will get? We'll get 0, 0, 0, 0, 0, 3 into 0, 0, 2 into 0 again 0, again 0, 1 into 0, 0, and 0 into 0, 0. So this y of 8 is also equal to 0. And finally, we'll do it for n equal to 9. So what do we get? Now we'll shift it here. So we have 1, 2, 2, 3, 0, 0, 0, 0, 0, 0. So again, we have a 0 here, 0, 0, 0, again 0, again 0. There is no overlap in any point. So at all points it comes out to be equal to 0. So this y of 9 is also equal to 0. Now if I shift it again by 1 unit, so I'll have 1, 2, 2, 3 and zeros everywhere. That is exactly equal to the value that we got for n equal to 0. Same thing we will get. Okay, so therefore the circular convolution is also a periodic quantity. So after little n equal to capital N, it just starts repeating itself. So finally what we get, so the 10-point circular convolution of x of n with x of n is given by y of n is equal to, we have 1, 4, 8, 14, 16, 12, 9 and 0, 0, 0, 0. So we have 1, 4, 8, 14, 16, 12, 9 and 3 times 0. So we have a, this is at n equal to 0. Is it clear? Any point? Any problem? Any questions? Okay. If there are no questions, then let me move on to the next question. So the next question here says that what is the smallest value of p for which a p-point circular convolution of x of n with x of n is equal to the linear convolution of x of n with x of n. Okay, so let us try to figure that out. What we want, linear convolution of x of n with itself. Now, if x of n is of length L, then linear convolution will be of length L plus L minus 1, that is 2L minus 1. This is a standard thing, we have seen this earlier as well. Okay, so this is what we have. Now this linear convolution should be equal to your circular convolution. Linear convolution should be equal to p-point circular convolution. Now what is the problem of circular convolution? Let us go back to the 4-point TFT. So now the circular 4-point circular convolution, so the problem is it is getting overlapped at every iteration. So if I have 4-point circular convolution, I'll get a 4-point valued answer, and there will be overlap at every point. Now we don't want overlaps at every point when we have a linear convolution. So in linear convolution, the overlap starts, it gets maximum, and then it again reduces. The overlap reduces. Something similar is happening in this particular thing in 10-point convolution. Initially, there is very few overlap. Then slowly, when we increase the value of little n, the overlap becomes maximum for y equal to 3 because it is a 4-point signal. and then again the overlap slowly starts to reduce. So here only 3 values are overlapping, here 2, then here 1, and here, and then again it reduces further, and here then there is no overlap. So we want something similar, or rather if we just focus on these first 7 values, or yeah, first 7 values, these are exactly the linear convolution of whatever we have found out, or of the given signal, 4-point signal. You try it out at your end, but we have these additional zeros which we can anyway discard afterwards. So now what we are interested in is we want the smallest value of p, for which my p-point circular convolution will be equal to my linear convolution. So now if I just focus on this part, and if I just take a 7-point circular convolution, I will land up in this one. If I take 6, I'll start getting overlaps. But if I take 7-point circular convolution, I won't get overlaps. So for any value of p which is greater than 7 in this particular case, we will get no overlaps at after little n equal to 7, and we can take the first 7 values of my circular convolution as equal to my linear convolution. So therefore, if I want linear convolution to be equal to p-point circular convolution, then this p should be equal to the number of points that we get in the linear convolution. So this p for this, p should be equal to length of the signal that we get after the circular convolution. Sorry, linear convolution, not circular. So therefore, this p should be equal to 2l minus 1, minimum value. Okay. So now for our case, L is equal to 4. So therefore, P comes out to be equal to 2 times L is equal to 4. Yeah. 2 times 4 minus 1, which is 8 minus 1, which is equal to 7. Okay. Is this clear? Any questions at this point? Okay, so this is all I wanted to cover today. If you have any questions, you are free to ask them right now in any part of the questions that I have covered today. You are free to ask the questions. Again, I'll reiterate that I'll be taking a summary session soon in this week. If you have any queries, then please post them tomorrow by 11 p.m. or by 12 a.m. midnight. So if you have any questions, just post them in the Q&A portal. I'll take up those questions in my summary session and try to help you out with those queries before your exam. So this is all from my side. Thank you for attending today's and all the other sessions. Hope to see you all in the summary session as well, and all the best for your exams. Thank you.